Okay, heat recovery in the data center. So to put this into context, I run a computing cluster at Queen Mary, and we are one of the sites that does the processing of the data for the LHC. And we've been doing it for 15 years. Our data center that we originally built was 15 years. It was built to a budget. That budget became increasingly clear 15 years later. The size of the cluster is about 17,000 job slots, 20 petabytes of storage, and we run about 175 kilowatts in total. This time last year, before the refurbishment, couldn't run 175 kilowatts, had to turn a chunk of our computer off because our cooling just didn't work anymore. So hence, refurbishment of our data center, and exactly how we did it. So, as I say, we're supporting the LHC computing. That project is planned to go through to, actually, I think the latest timetable is to 2040. And so if we're going to support it, we need a solution that's going to run for at least another 15 years. And our other objectives within our data center was to increase the capacity, to increase the efficiency, to improve the resilience, and to reduce the environmental impact. So a very clear, simple set of objectives. We're not dictating solutions at this point, and we're not dictating PUEs or anything like that. We're just going to basically see what we can afford with the money we have. Actually, before I get on to the design, Chris will know, because it took 2 or 3 years of discussions within us to work out what the solution was as we iterated and we worked out how much it was actually going to cost. Eventually, we came forward with this design. So we're going to have a room reusing the old data center. It's going to contain 39 racks as an average of 10 kilowatts a rack. So that's quite low modern standards, but we can be a bit flexible, so we can go up to 20 kilowatts with the 4 single-phase PDUs we have in each rack. Or we can go redundant 10 kilowatts because we've got AB power supplies. We're using hot aisle containment with in-row coolers, and we've optimized the temperatures of the water coming in and out and the air in and out so that they are what the manufacturer says is the optimally efficient for the cooling to get the best efficiency and power. But you might notice 45 degrees in the hot aisle is fairly hot, so I have been buying my computers with front-facing VGA and USB ports in the cold aisle, so I don't have to go in the hot aisle too often. We have a fire suppression system, so dropout tiles. We do not have a raised floor in this room, so that means all the power and cooling has to come from overhead. That's basically a cost thing. We couldn't really afford to build a raised floor, and actually the space in the room doesn't allow for it as well. You'll see some pictures and you'll see some columns that get in the way and so on. That's just annoying. We connect to the building management system in parts with the Modbus system. And at the end solution, we were using APC hardware throughout, and we're using the data center expert to monitor the room inside the room. And then just as a picture of the room, what it looks like, you can see the facility, cooling water coming in from the left. At the top, it's above the door, and it goes above the hot aisles. And then on the far top right, you see the power coming in from the data center. So we have 2 feeds, A and B, to each rack, providing us with our power and various other facilities in the room. There is 1 rack which has been dictated as the room infrastructure rack. So that contains basically the switch, data center expert monitoring, some UPSs and so on for managing the room and the network in the room. And then just a couple of pictures. So on the left, you see the room as it was emptied. So essentially for this project, we had to turn off the data center after 3 months. So we couldn't run for 3 months. But for us, that's not a problem because we're doing the LHC. There are 5 other sites in the UK, 100 other across the world who can pick up the slack for those 3 months. So we were not missed for 3 months, but we would have been missed for longer than 3 months. So the room left as it was emptied, and then about 6 weeks later, you see what happened on the right. So we've already got our cabinets, our containment for the hot aisle, and you can see above the racks the power and the cooling. A better picture there, just showing exactly what it is. So this is taken before the cooling was lagged. So the cooling pipes get lagged to protect them. And then this plot shows on the day we were decommissioning the rack. So you can see at the top the lagged pipes. And if you notice the yellow fans in one of the racks, that's a heater. So we basically had a 200 kilowatt artificial load in the room to commission and make sure everything was working to that level. It wasn't possible to get all 390 kilowatts in one go. So that was in the room. Interesting stuff upstairs. So in the plant room, because we have a chilled water circuit going through the in-row coolers that do the cooling in the air or in the data center, that chilled, not so chilled water goes back up into the plant room. So at 23 degrees. Then we have a cooling capacity of 390 kilowatts. To do that, we have 3 200 kilowatt water source heat pumps. So we have an N+1 redundancy there, and that takes that 23 kilowatt and puts it back to 17, which will then go back downstairs. And then that also produces what we call a high quality hot water circuit of basically 75 degrees, which can go directly then into a district heating system via a heat exchanger, which is very close by. If it can't go into the district heating system, we have then 2 300 kilowatt dry air coolers outside, which we can put it to the atmosphere. And that can work all year round because the water going into those dry air coolers are 75 degrees. To put that into some kind of picture, this is what is happening. The cluster produces hot water into the heat pumps, goes into the hot water store, so we can store it in the room, into a heat exchanger, into the district heating system. They have additionally been building additional water tanks around campus, so they've got several 3,000 litre tanks to store the water. There's about 10 buildings presently connected to the district heating system, including residences and catering departments. So the water isn't just used for heating, but it's used for hot water. It can be used for showers for the students. It can be used for hot water for the catering department. So it is actually being used all year round. And then this is what it looks like upstairs in the plant room. You can see that the space is quite tight, and actually the 390 kilowatts I mentioned is basically somewhat being driven by the amount of space we have available in the plant room to install the kit. So we have water tanks, heat pumps. Then in the middle, we've got the heat exchanger, and then on the right, you've got the dry air coolers outside. So what did we do? So we increased the capacity of the room. So we had 15 racks. We went up to 38, or usable racks. One of the racks has a bollard in the way, fortunately, for the building. We went from a nominal 150 kilowatts under room to 390. We've got a flexible rack, so we can go up to 20 kilowatts a rack. And an additional, the original racks in the room were only 800 mil deep when they was first built. And we now have 1200 mil deep, which is much more useful for modern kit because a lot of modern kit needs that 1200 millimeter deep racks. We improved the efficiency. So as I say, we didn't aim for a particular PUE in the room. But we went to aim for using best practice, so hot aisle containment and as such. We went from using refrigerant cooling to water cooling, so there's an improvement in that, but also that's good for the environment. Hot aisle containment, as I said, is considered one of the best solutions for this sort of build. We chose the temperatures differentials, the temperature deltas, to be optimal for the cooling and efficiency. We do not have UPS in this room, and we do not have a UPS for the data center as such. If you need a UPS, you have to put it into the rack yourself. That's partly because, again, with the LHC, if we have a power glitch or we have to power down, we can cope with that because the slack gets picked up elsewhere. If you didn't have that flexibility, you would need to have a UPS room. And then what's happening is machines from other campuses, so EECs, or electronic engineers, they're starting to move their kit into the room in the extra capacity. As I say, we improved resilience, so we have an AB power supply for each rack. We have 5 in-row coolers per rack, so that's actually 4 + 1. So we've got an additional extra in-row cooler, so we can take one the in-row coolers out of service. If that happens, we've got 2+1 heat pumps. We've got alternative options for the heat exhaust, the dry coolers, or the district heating system. As I mentioned, we have no backup power generator or UPS for this room, but the equipment in this room doesn't need that level of resilience. It would have cost a lot more as well. Reduced environment impact. So we've got the improved efficiency. We're doing the heat recovery. So we're using the heat from our system to heat the university. So over the winter, we've been running at about 200 kilowatts in the room. And talking to the estates people, basically the 2 buildings have not used their gas boilers all winter because of this heat. So the chemistry building, which is the least efficient building on campus, and the Queen's building, which is the oldest building and the second most inefficient building on campus, haven't had to use their boilers. So of course, moving from gas heating to electric heating, well, the electric is 50% carbon, low carbon sources, wind and recyclable. So we have a lower carbon cost, essentially. And we're using, as I said, water rather than refrigerant gas, so there's some improvements there. So some observations of the project. So having a clear of achievable goals. So those simple set of objectives was actually important, because each time we made a choice about what we were doing, we basically referred back to, are we doing those, are we delivering on those achievable objectives? Second one is project management. So my experience of project managing is IT project managers, and they're not very good. But this is an estates project. And the estates project manager we got was actually very good. They weren't specialists in data centers, but they knew their business in cooling and electrical and civil works, and they were able to bring it all together and get people to work, and the right people to work. And so that was actually really good to see somebody actually do that job. And the financial case. So we had to make a financial case to the college to define it. So we had to put that all together. To do that, we in part used the green book from the government project management stuff, so to define to get the costs out. So that was useful in order to build up a case to do this work. The total case amount of money this project costs in the end was about 2.5 million, of which an extra $1 million, I guess, was going for the full heat recovery solution rather than essentially reusing cheaper chillers, traditional revision chillers. So what do we have on the DC build? The reason I chose APC is because we had a lot of APC kit to start with, and so we could reuse it. We did reuse a number of racks and PDUs to get to the price down. I said no raised floor, so there is a concern there of having the water and the electricity above our racks. And there's no UPS, and there's no backup power generator in the room. So one of the issues that we had with the old system was that essentially was no monitoring of the room. So basically, the only reason we knew the cooling failed was when our servers turned off. The new system has a lot better system. We're integrating into the building management system, and there's a significant oversight now from the estates people into making sure that room works all the time. So that's an important part that has improved the resilience of the room. But as I said, there are a few future concerns. So as I said, the old data center declined quite quickly over 15 years. We don't want that to happen again, because this room probably needs to work until 2040 at least. There is a concern about the leaks. We have water above us. If it leaks onto the servers, that's a big problem. We have leak detectors installed and a monitoring system with alarms. And it isn't the highest density system you can go now. Some modern data centers are talking about 40 kilowatts, 80 kilowatts. This is clearly not going to be for that sort of equipment. So it is within its scope. It's doing what it can. It's not 100% awesome yet. We have had one leak within one of the in-row chillers, and actually, which wasn't very nice. We only saw it once we had a maintenance day, so it turned off the heat from the computers because otherwise the leak was at a low level that it was just evaporating off. It's proved difficult to get the building management system to manage the heat pumps accurately. The heat pumps occasionally send sort of error messages, and just dealing with these sort of non-standard situations has proved complex, but we've been getting there. And as a result, we had a few trips that had seen high rises. So we prepared for this. We have a system that turns off the cluster if it gets too hot. Yeah, so that's a water leak that comes from an in-row chiller on the floor there, which was unfortunate, but it didn't hit any of the computers. It just was in the in-row chiller going straight down. So in the end, it wasn't a problem. So at the moment, we're operating since November. We're operating at about 200 kilowatts. And basically all that heat is going into the district heating system, so it's already being reused. And I have to say, I didn't appreciate how complex an infrastructure project is when we started. When I do a project, it's just me and a few other people and we get on with it. But to see how many people and how complex it was to organize was interesting and the learning experience. And of course, there were lots of small things to do at the end, doing things like the alarm assessments, alarm thresholds, cable management, which of course always drags the project down, which is what I have to do at the end of the project. So yeah, but that's what I want to say.
Take your cybersecurity to the next level at this year's security conference. Taking place across the 25th and 26th of November, this year's event is about coming together as a community to strengthen our resilience and shape secure, sustainable long-term success. Each of our member and customer organisations is eligible for 2 free in-person tickets for this year's event. Please speak to your relationship manager for further information. So don't miss out. Join us in Manchester this November for 2 days packed with actionable insights, CPD accredited learning and fresh new ideas to help drive sustainable progress and shape a secure digital future for our sector.
Welcome. I'm just going to talk a little bit about direct liquid cooling, some of the reasons why you might use it, and especially some features and quirks you may have not discovered yet. So, main reasons for considering DLC, I think you'll find cooling requirements now getting a lot more dense. Water temperatures, we can run a lot higher, so there's heat reuse is a lot more achievable, and a little bit about chillers. So, heat capacity. As you can see up there, heat capacity of air, it's not brilliant, it's not bad, but using water is a lot more efficient way of getting rid of the heat. And as you can see up the top, there's high density air systems, one of those DGX units, one of the latest ones, one of those NVIDIA Hopper ones, is 15 kilowatts in 8U. It's a lot of heat, and you're going to get 60 kilowatts a rack. That's about the limit of those air cooling units, and they're going to sound like a jet turbine. You don't want to be near them. So high density now, we're going to get even higher. If you look at putting DLC units in, you will be looking at up to 100 and something kilowatts in a rack from those units now. And they'll be a lot quieter, but still hot. So water temperatures. You'll find with DLC, you can get a lot higher water temperatures. Most of the DLC equipment will happily run at 40 degree input temperature for water. Some of them will even run higher, so you can get away with a lot. Return temperatures, 60C is about average these days. If you're pushing them hard, that 60C water, as you can see from the previous talk, is actually a pretty much usable temperature for a lot of things. So good returns on that. So if you're trying to use lower supply temperatures, you can have a lot for air, you can have a lot lower water temperature. You'll see there's some differences there. So basic system for chilled water. We often use it for air cooling and DLC now. Here's a picture of both. On the DLC, you can get away with a much more passive unit. These can be just free air coolers or water sprayed as well to give a bit of extra performance. You'll find these give energy efficient ratios of 74 to at 90 each to 1, against the traditional methods of 4, maybe 4-ish. Depends how efficient you've got one. So this is basically due to water temperatures, air temperatures, and everything else. Main thing to notice is DLC, your free cooling coils, you can get about ambient plus about 1 degree. And if you're lucky with spraying water on it, you'll get about 10 degrees below ambient. That does become important later on. So, consequences. Some of these consequences and considerations once you've actually got a DLC system. Your plant room. You've now got potentially multiple isolated loops because you're going to generally have a different water composition inside from outside. You may have got away with it in the previous sort of examples where you're doing air-cooled with liquid. You'll generally have a loop. In DLC, you'll generally have heat exchangers of some form to actually isolate the outside loop and the inside loop because they've got different parameters, needed chemical makeups and things. Now, because we're running a lot higher water temperatures, we've got a Legionnaires problem. I'm sure your estates department will love to talk to you about Legionnaires. I don't. So the other thing is, all this extra complexity in the plant room, you've got a lot more space. I mean, that picture up there shows 3 loops, and it's all complicated, twisted together because someone expanded it a little bit and it didn't fit quite what it was supposed to. So more plant room needed. Now, these CDUs, these fundamentally transfer your heat exchange from your liquid cooling loops into your outside loops or whatever your chillers or however you're getting rid of your heat. Now, CDUs basically let you take the control from the estates department and put that back into your control for actually managing the loops. So normally outside loops are controlled by estates. When that's all going into your equipment, it's all estates problems and all estates configurations. These CDUs allow you to change it so that it's actually, you can tweak things inside differently from outside. So fundamentally, you've created an isolated loop between the outside chiller and you. I've got 2 examples of CDUs here. The one on the right as you're looking at it is a large 600 odd kilowatt designed for multiple racks. The one on the left is actually an in-rack unit designed for a couple of 100 kilowatts, just put it in the rack. They're all fundamentally the same. They have slightly different resiliencies, but generally you'll find they've got heat exchangers and pumps in them. So you've relocated all this equipment from the plant room now into your IT space where you have control. They're intelligently controlled systems. They're designed to be actively adjusted and very flexible, so you can tweak how much equipment goes into them and they'll adjust and you can configure them. So in rack 1, you get a limited capacity of the unit, smaller number of nodes connected to it, but if you've only got a few, it's quite convenient. You need less flow rates and things through them. Whereas on the right, it is the size of a rack, as you can probably tell, with all the equipment in there. And one downside of having this is you do actually have to get maintenance on them, and your engineers will have to come in here. There's people that, hopefully don't spill the water everywhere and everything else. One thing, keynote about this is service contracts. You want to have some service support contract on this, because if this breaks, you have no compute working. So, one of the things about DLC, you'll find, is that only a certain percentage of the cooling is effective. You're generating so much heat, and most of that goes into the DLC loop. Some of it doesn't. Traditionally, it's been things like power supplies, some of the network equipment, hard drives, etc. doesn't go in there. Initially, about 5 years ago, they were saying it's about 20% you don't get in the DLC loop. You have to still go to there. Now, they're now saying you can do about 100% with a little asterisk there. Basically, you put the right components in. They've now cooled it. They now put direct liquid cooled loops and little heat sinks, things, all going to all your other components like your power supplies, your RAM, your SSDs, etc. So that's the proposals. Next generation stuff should be that, and they claim to be 100%, but there's definitely a passive amount of radiating heat coming off that, so it's not truly 100%, but it's near enough. So that remains in heat. As I said, you could be talking 100 kilowatts a rack. Well, 10 kilowatts was used to be a rack amount of power you had. Now, 20% of 100 kilowatts is 20 kilowatts. As you heard from Daniel earlier, that's his total rack output, and that's just the excess coming off this equipment. So you could actually have a significant amount of heat still being generated into your room. So you're going to look at some other solutions. So we've got things like passive rear doors, good for about 10 kilowatts or so. After that, we'll probably need to upgrade to actually active rear doors, because the airflow going through them, you'll need to pull more through them to get better efficiency after the cooling. Or you can actually just go, like Daniel had, with just the traditional hot aisle, cold aisles, in-rack coolers, etc. You will just generate some heat, and you'll have to get rid of it in the traditional ways. So room temperatures. As we've said, we could do 40-degree water temperature input. Well, if your rear cooling doors at the back are getting 40 degrees in, for cold water, your room is going to be 40-odd degrees warm. It's lovely if you like the tropics. Most people don't. And unfortunately, there's things called hard drives that we all kind of use still, really hate 40 degrees. You've got about a 35-degree limit on a hard drive. So what this means is you're either going to have an all NVMe SSD system, and that won't care too much about the temperature, because interesting enough, SSDs actually like a bit warmer temperature. They work slightly quicker, slightly more powerful. But if you've got hard drives, you're going to have to soon to think of some other way of coping. Are you going to have another room? Are you going to have some little micro data center or something that just keeps your hard drives in it and keeps them nicely environmentally cooled? So you've got a different environment spec. Tape libraries, for instance, have an even worse environmental spec, about 25 degrees they like. So these days, you're now looking at data centers with 2 or 3 different temperature environments. Water quality. Well, as we said, we put water around this system. All these nice warm 40 to 60 degree temperatures. Bacteria loves growing in those temperatures. It's lovely. It's the perfect range, apparently, according to our water experts. So you have to treat it. You don't want bacterial growth. You don't want them to be the new generation of some bug that's unkillable and growing everywhere. So you have to treat it. There's lots of treatments you need. Chemical treatments to stop you growing the bugs. Chemical treatments so you don't eat all the pipework and metals and all the other nasty stuff. If you look at these pictures, the picture on your left is a sample that's settled. When it was shaken up, they look like the ones on the right. You can see we've actually managed to get horrible little bits in them. In some cases, it's little fine particles. Some cases, it's little bits of bacteria. Yeah. So these are things that can cause problems. As you can see in the middle, I've got an example of a heat sink. This is actually not one of the HPC systems, but it was a nice one that I could show you what it looks like inside. They're tiny fins, less than a millimetre sized gaps. Doesn't take a lot to block these. These tiny little particles, bacteria, etc., algae growths will block it. And that will restrict your water flow through it. That will restrict how much cooling it can do. That'll also possibly make the thing crash randomly for you. So purely, these systems need a lot of water flowing through them. If you don't get the water flowing through, they don't cool. So if they get bunged up, parts of them may overheat when you're doing certain operations, and they'll just randomly crash on you. So you need a very good water solution, and you need to make sure it's sampled and checked appropriately at regular intervals. And any potential issues, you actually go and check it out and get it cleaned, flushed, and rectify the problem. As I say, we're talking about heat rejection. As I said, water has to flow through these tubes. We've got a lot of pipe work underneath. You can measure the water flow rate. Everything is based on water flow rates and water temperatures. So you have to calculate the flow rates. Generally, you'll calculate it across a known pressure drop, based on cross sections of your pipes and everything else. Tools on your right can measure them. They're expensive little tools. They'll measure the different pressures. There you can work out your flow rate, and you can work out if you're within specifications of the manufacturers. Roughly, the thing we use as a back of the envelope calculation, about 1 kilowatt per litre to flow rates is what we roughly work out. It's a ballpark, a good start. So, if it's not working right, you have low flow rates, well, all goes horribly wrong, as I've said. These heat blocks are compact. They've got a low thermal mass. These examples here, there is a system at the bottom. I think that one's one of the supercomputers in USA, from memory, from that picture. I think it's one of the HPE nodes. That, as you can see, is 1U high. All those heat blocks in it, all that pipe work, there's that plastic on the top, and there's a tiny little bit of metal copper on there. The one above is one of that's an H200 node, might be an A100 node actually, think about it. At the top, 2 CPUs on the right, 4 GPUs on the left. GPUs and CPUs are in parallel in that, and so is the memory, but the water is flowing through it. If anything bungs, the heat sinks up. So if you get a growth or something stocking your heat top chip, it may restrict the flow for the later ones. So you can actually find a problem when one causes problems down the line. They're relatively parallel, but they're not all parallel. So it's unpredictable. Unstable units. One of the comments that I've got up there is power limits. All these GPUs and things, they have intelligent sort of clocking, down clocking and everything because they get hot. Sometimes this heat generates so quickly, the sampling rate of the systems when they're checking, oh, you're getting too hot, can't keep up. And they will actually crash because the sampling doesn't keep up with it. So it gets too hot, crashes, dies before the next sample comes in. It's very hard to detect. As I said, it's really fast measurement. You're pushing out hundreds of watts at a time, and that changes very, very quickly in these systems. So you really can't tell. It is really part of a gut. Is that likely to cause it? Increase your flow rates, have a look at things. So one thing I've also got here, racks. Racks are getting heavy. I think we're all aware quite how heavy it is. It's even worse now with liquid cooling. All this copper is heavy. We're now getting really dense amounts of it. And on top of that, we've got water flowing through it as well. So there's water, there's pipes. It's all just adding up. So we've got racks now, at least 1,500 kilos a rack. Easily 1,500 kilos. They're probably about 1,600 kilos now with water in and everything ready running. So people are now considering not using raised floors anymore because they've got a limited weight limit. So actually put them back onto your concrete slabs. That's got a far better, tougher limit. If you've had your slab built correctly, that is one thing you have to check. So now raised floors is getting more common straight onto the slab for that reason. It's managing point loading as well. I've got a few minutes to talk about some real world situations I've discovered, seen, been involved in, heard about. So power considerations is another one now. You're often feeding, certainly for those DGX units, 6 power feeds a rack. Partially because most of those units have 6 PDUs in each. And therefore, if you fly 6 feeds to it and you lose one feed, your equipment doesn't go out. Whereas if you had 4, it would take the power maybe, but actually in a failure node, it's not just a half work, you need 5 out of the 6 working. So that will actually, you'll put more money now into putting more PDUs in the racks to actually take that load across. They'll often be single phase, 32 amps. But generally, you may have problems with that because actually those 32 amps often get split into 2 feeds, and therefore you've got 60 amp a feed, and your units are needing 10 amps each. And 10 amps into 60 amps only works once, so you may end up looking for different PDUs or actually a higher power rating, so you can split it better. 63 amp 3-phase are not uncommon. Certainly for the non-DGX systems, you'll often find them now being used. As I said, they've got so many power supplies per unit, you can get away with that. So a few things looking forward, looking forwards. It's different from what we're used to. But, water cooling for air systems, that was unusual 10, 20 years ago. Now, we've seen. It's now what everyone considers just standard. We've got lots of other considerations to look at for those niggles, problems, concerns, maybe things you haven't thought about. It's a learning thing. We're all learning. This data center I know about were put in 8 years ago. Papers about how to do it were written 6 years ago. So there is a lot more being learnt day by day. And this is the new upcoming way. I have to say, I think it's probably the future for those high density systems. You'll get away with it air for a while, but the air units are going to get bigger, noisier, heavier, and you'll get less of them in a rack. But maybe you've got enough space you're not worried about. But if you want the high density, you want the much more efficient cooling systems you can get, you can heat reuse, you can just put free coolers in and not worry about it 99.something% of the year, DLC is possibly a way to go. It's more complicated, more people will start using it. Hopefully, in another 10 years, it'll just be common knowledge again. So, thank you.